In this lecture, we're going to lay the foundations of real exponents, and we will rigorously define and prove what it means to take the real exponent of a real number. Because so far, what we have done so far is we have defined what it means to take a rational exponent of a real positive number. So for example, if we have a real positive number a, and n and m are integers with m which is non-zero, then a to the power of n over m is the m's square root of a to the power of n, and you can see that it's well defined, even if both of those or one of them is negative, because if the exponent here is negative, that means that we need to take the reciprocal of a and then do the same operation, but this is well defined. So whenever we have a rational number, we have a pretty good understanding and idea what it means to raise a to the rational power exponent, such that it has some nice properties that we've established previously. But the question is, how would we define a to the power of some real number alpha when alpha is irrational? We know that are irrational numbers, and therefore they cannot be presented as this fraction, right? There are real numbers such as pi or such as square root of 2, which simply cannot be written as the fraction of two integers, right? So what would we do in this case? And so the idea that comes to mind is that we can pick a sequence of rational numbers that would converge to this number and then take some limit in the process. And this approach actually works. This is the approach that we're going to take, but there are many difficulties that we'll have to overcome and things to prove before we lay the foundation. So this is going to be a bit technical. It's actually going to be very technical. So the first idea that comes to mind is how are we going to define a to the power of alpha? Basically, it's going to be this limit of a to the power of qn, where qn is a sequence of rational numbers that converges to alpha. And basically, we know that the rational numbers are dense in the real numbers, and every real number is the limit of rational numbers, right? So it's not a problem to pick a sequence of rational numbers that would converge to any real number. And then we need to take this process. However, since there are infinitely many sequences of rationals that converge to any real number, right, we'll have to show that this approach actually works, and this is well defined, and this is independent of the sequence that we pick, right? So this is gonna take some work. Okay, so first of all, this approach works, and we have to prove that this is well defined and that the limit is independent of the sequence of rationals that we choose. And for all such sequences qn of rationals that converge to alpha, this limit is going to be the same, and this limit would be how we define a to the power of alpha, which is the real exponent. Moreover, one more thing that we need to recover is that whenever this real number alpha happens to be rational, then this new definition has to coincide with the previous definition of exponents of rationals, right? So in this case, you can say, well, yeah, obviously I can pick just for a rational number a constant sequence, which is this number, and it would converge. And this is exactly like we're going to show it. So I'm jumping a bit ahead. So let's do it step by step. So what would be the first step? So first step, we'll assume that alpha is positive, and we will define a to the power of alpha. Basically, this also covers the case where alpha is negative, because for negative alpha, we'll just define a to the power of minus alpha as the reciprocal of a to the power of alpha whenever alpha is, positive, in this way. Okay, so let's proceed. All right, so what we can do is we'll start by choosing a sequence of rational numbers that is monotonically increasing and converges to alpha. And basically, it can be done. There are lots of ways to construct it, and I chose, for simplicity, the most direct approach here. So we know that any real number can be written in this infinite decimal expansion, where it's m. M is some natural number, right? Non-negative. And then these are the digits of the infinite decimal expansion. This is the constructions of the real numbers that we're going to use here. And therefore, if we terminate this at every finite point, we're going to have a rational number, right? So the idea is going to be the following one. So every real number can be written in this infinite decimal expansion. Okay, and how can we define a monotonically increasing sequence of rational numbers that converges to this number? Basically, Qn is going to be this sequence. We start with this natural number m, and then we take the expansion of the up to the n's minus first digit. So this is an expansion of length n, right? And then this sequence is a sequence of rational numbers, because whenever we terminate at a finite point, this number is going to be rational, right? And this is going to be monotonically increasing because we add every time only non-negative terms. So this sequence is going to be a monotonically increasing sequence of rational numbers which converges to alpha. Okay. And then, okay, so Qn is monotonically increasing and the limit of Qn is alpha. And, okay, why do we need this? So maybe the hint would be is that we would want to use the monotone convergence theorem, and we'll see it shortly. Okay, so suppose for now that we have a monotonically increasing sequence Qn of rational numbers that converges to alpha, and we've shown how to construct such a sequence. Then we'll consider this sequence a to the power of Qn, okay, which is this infinite sequence. And since a is positive, this sequence is actually well defined, right? Because we know what it means to take a rational exponent of a real number. Okay. Now let us assume for simplicity once again, or just consider this case, where a is bigger than 1 and alpha is positive, right? This is the case here, okay? So Qn is positive as well, and for every n, this sequence is actually going to be monotonically increasing. Why is that? Here I'm using actually a well-established property of the rational exponents. If a is bigger than 1, then the bigger the rational exponent here, the bigger the value is going to be. Okay. So this would be actually a monotonically increasing sequence. Moreover, for every rational number q that is going to be greater than alpha, we're also going to have that a to the power of q is going to be greater than a to the power of Qn, because Qn is smaller than alpha, right? Alpha separates those two. And therefore, we have is the ideal setup of the monotone convergence theorem, which we would like to invoke here. And the monotone convergence theorem is heavily based on the key property of real numbers, which is the axiom of completeness. Basically, the whole constructions of real numbers, whenever we construct this any real number, we use the completeness property, because we construct the real numbers by completing the rationals, so to say, in one way or another. So it's the axiom of completeness that plays here the key role for this construction. Okay. So this sequence is monotone increasing and bounded above in case that alpha is bigger than 1. And if alpha is smaller than 1 but still positive, then the sequence is going to be monotonically decreasing but still bounded from below by 0. Okay, so the sequence is monotone decreasing and bounded below by 0. Okay, so in both cases, the monotone convergence theorem can be applied. And so whenever we have a real number a which is positive, we pick a monotone increasing sequence of rationals that converges to alpha, and this sequence is going to be convergent by the monotone convergence theorem, and then its limit, we'll use its limit to define what it means to take the a to the power of the real exponent alpha. Okay, so for positive alpha and a which is positive, we're going to define a to the power alpha as the limit of this monotone increasing sequence, and we just showed that by the monotone convergence theorem, this sequence is going to converge. Okay, so formally we now have the following definition, right? So the definition is for a positive real number a and a real number alpha, which is also positive, then a to the power of alpha, which will denote, of course, as a to the power of alpha, is defined as follows. Basically, the things that we said previously. We pick any monotone increasing convergent sequence Qn of rationals that converges to alpha. And then the limit of this convergent sequence, which we've proved that it's convergent by the monotone convergence theorem, is going to be the definition of the value of a to the power of alpha. Now we're going to prove that this definition is actually well defined and is independent of the sequence that we choose to converge to alpha, right? As long it is monotone increasing, okay? Okay, so for that, we're going to prove the following lemma. So we start with a lemma for a, which is a real number, a positive one, and a sequence of rationals that converges to 0, then a to the power of those rationals is 1. So it seems kind of obvious, but it's not so obvious to prove, of course. And I mean, along this lecture, I think there are going to be lots of moments that you're going to feel that we're proving the obvious, but the proof itself is not that obvious, right? So what we've proved previously in previous lectures, right, is that for positive a, right, positive real a, what we have is the limit of the nth square root of a is 1. Okay, so review the relevant lecture if you're not familiar with that. Basically, we're going to rely on this result. And so the same idea can be applied to a to the power of negative 1 over n. So by the limit arithmetic theorem, it follows that the sequence also converges to 1. Okay, so we conclude that this limit is 1 as well, and you probably guess that we're going to invoke some kind of sandwich theorem here. Right, and so how is it going to work? So since a is bigger than 1 and epsilon is positive, there exists a number k that depends on epsilon such that this holds. So basically, we're saying that this sequence 1 over k converges to 1, so it's going to be between 1 plus epsilon and 1 minus epsilon, and then this sequence is convergent to 1, so this inequality is going to be always valid for a which is greater than 1, and basically we can choose n that is big enough such that a to the power of 1 over k is smaller than 1 plus epsilon, and this value is going to be greater than 1 minus epsilon. So therefore, for every epsilon, we can find a natural number k of epsilon such that for every k greater than this k of epsilon, this holds, right? This is just the definition of the limit. Okay, so now since this sequence of rationals that we started with, which converges to 0, since it converges to 0, eventually it's going to be smaller than 1 over k, and then a to the power of our n is going to be squeezed between those terms, right? That's the key idea of the proof. So now there exists n of epsilon, right? Since our n converges to 0, then there exists n of epsilon, which is actually n of k of epsilon, right? Because basically we can choose this epsilon to be 1 over k, right? Because we want our n to be squeezed between those two numbers, and since our n converges to 0, then there exists n of epsilon such that for any n that is greater than n of epsilon, which is this k of epsilon, right, this holds. Okay, that our n is between minus 1 over k and 1 over k. Okay, and therefore again we are invoking the property of the rational exponents. So since a is greater than 1, and all those numbers are rationals, we know for rational numbers that a is greater than 1, then the bigger the exponent, the greater the value. So we have this chain of inequalities here, which shows, essentially we have shown that for every epsilon, there exists a number n of epsilon, such that for every n that is going to be greater than this n of epsilon, a to the power of our n is going to be between 1 plus epsilon and 1 minus epsilon. Therefore, this means that the difference between a to the power of our n and 1 in the absolute value is smaller than epsilon, which means that the limit of a to the power of Rn is 1 whenever a is greater than 1 and Rn converges to 0, right? So we're past that, but and the case where a is between 0 and 1 can be handled the same way by applying it to the sequence of to the real number, which is 1 over a, and then applying the limit arithmetic theorem. Okay. So now we're going to prove the following inequality, which is very useful. We've actually proved versions of this inequality in previous lectures. So the inequality that we're going to use extensively here is called the Bernoulli inequality. And basically in previous lecture I proved that for x, which is just non-negative, with the binomial formula. But now we need the full extent of this inequality, and we'll prove it for x that is greater or equal than -1 and any natural number n. The following inequality holds. And let's see some intuition of how it behaves and how this inequality looks geometrically. So let's see the geometrical intuition behind Bernoulli's inequality. Basically, for n equals 1, we have two curves here which coincide. Why? Because when n is 1, this is 1 plus x, and this is 1 plus x to the power of 1. So when I plot those two curves, they basically coincide, and we get this straight line. But it's interesting when we increase the exponent here, n to 2, for example, what we have is that this line is actually tangent to this parabola, and this parabola is bigger than this straight line everywhere. And what remains invariant for all the families of curves is that this point of tangency, where x is equal to 0, then both functions attain the value 1. So this remains for every exponent n. Basically, as we increase n, you can see that the tangency condition is remained for all the family of those curves, right? And another thing to note here, then, clearly for even exponents, this function is going to be greater than the straight line absolutely everywhere. However, in the setup in which we prove this inequality, x is at least -1 here, right? Because there is some breaking point here. If x is negative, then there is some breaking point here in which the inequality is no longer valid. And as we increase the exponent, the point in which this inequality is breaking is getting closer and closer to -1. Therefore, if we want to be on the safe side and know that this inequality is valid for no matter what the exponent n that we're using, then we need the restriction that x is at least -1. And you can, maybe if you want, you can generalize it that for even exponents, then this inequality is valid for every x. And for odd exponents, you basically have to impose the condition that x is at least -1. It's somewhere behind -1, but it's not the focus of the current discussion. The important thing is for you to see the geometric intuition behind this inequality, and I think that this tangency condition being preserved in those two curves as they evolve is very beautiful. So hopefully you got some intuition as to how Bernoulli's inequality behaves, why it is correct, and what's the intuition behind it. And with more advanced machinery from calculus, it's going to be a straightforward proof with the tangency condition. However, since we have not developed all this machinery that is required from calculus yet, we'll develop it in the course in the future, we're going to prove it by induction. Now that we've seen the geometric intuition behind Bernoulli's inequality, let's prove it, and the proof is going to be straightforward by induction. So the case where n equals 1, we've seen it in the visualization. Basically, those are the same functions. So this inequality is valid for every x. So this case is just trivial, right? And so the inductive hypothesis, we assume that for some value of n, this holds, and then we need to prove that if this holds for some value of n of k, right, or some value of n, then it holds for its successor for k plus 1. And that's what we're going to prove. So we're going to prove it for n equals k plus 1. And this is the part where we're going to use that x is at least -1. Why? Because we are going to multiply it
by 1 plus x. That's inequality. Basically, you're not allowed to multiply both sides of an inequality by 0. I mean, it could be 0, but then in case it's 0, then we are on the safe side because we have the equality here anyway. So it doesn't change a lot. So yeah. So multiplying by x plus 1 both sides, since this is sides of inequality, since this is non-negative, we do not have to reverse the direction of the inequality. Okay, so in the following step, so by the inductive hypothesis, this is valid, and then multiplying both sides by that, since this is non-negative, then it becomes valid because we don't need to switch the direction of the inequality. The direction remains the same. Even in the pathological case where x equals to -1, we get equality on both sides, right? If we now open the brackets and expand, basically what we have here after expanding the brackets is, once you open it, is this. So it's 1 plus k plus 1 times x, and this term is non-negative because we assumed n to be a natural number. So k is an integer, okay? And so this is non-negative since x is at least -1. Then we have proved this inequality by for the next value of k, k plus 1. Therefore, we have proved by induction the inequality, right? So since this inequality holds for 1, and then since it holds for 1, we prove that it has to hold for 2. If it holds for 2, it has to hold for 3, etc. So this completes the inductive proof, right? Okay, so now let's prove a theorem. And for the proof of this theorem, as you imagined, we're going to invoke Bernoulli's inequality. So for a, which is a real number, and alpha is another real number, the value of a to the power of alpha is well defined, which means that it's independent of the sequence of rationals that we chose. The sequence of rationals that we chose to converge to alpha. Okay, so let's start the proof. So whenever we have a sequence Qn of rational sequence of rational numbers that converges to alpha, and we'll pick another sequence of rationals, which is going to be the monotonically increasing sequence of rational that converges to alpha, and basically we can choose if we want to the decimal expansion up to the nth place, right, of alpha, right? We expand alpha into this infinite decimal expansion, and then we stop at the nth place. So we get a sequence of rationals that converges to alpha. And so by the arithmetic theorem, then this limit is going to be 0. Okay, and now what we're going to do is we're going to apply the previous lemma, which, okay, we'll see how. So a to the power of alpha on the one hand is just defined to be the limit of a to the power of sequence of rationals, which is monotonically increasing to alpha. Okay, and on the other hand, this sequence a to the power of Sn minus Qn, we've proved, actually, that was the essence of the previous lemma, that this converges to 1. So this is a convergent sequence. So we can invoke here the limit arithmetic theorem. Basically, what we've written here is this limit is 1. And times this limit, basically, we have an inequality here. But now, since the sequence converges to a finite limit, then by the limit arithmetic theorem, this equals to the limit of the product of the sequences. And then by law of the exponents, we conclude that this is just the limit. This product equals to a to the power of Sn. So what we see here is that Sn was an arbitrary sequence of rationals that converges to alpha, whereas Qn was some sequence of rationals which is monotonically increasing and converges to alpha. And what we see that from here is that for every sequence of rationals, monotone or not, a to the power of Sn would converge to the same value as a to the power of Qn, and this is how we defined a to the power of alpha. So now we have a bit extended our reach, and now we can use any sequence of rationals that converges to alpha and take the limit, and we'll get the same limit. We are sure to get the same limit. So now this is well defined, because previously we defined a to the power of alpha as this limit of monotonically increasing sequence of rationals. But now we have proved that the limit is going to be the same, doesn't matter which sequence you pick. So this is well defined and is independent of the chosen sequence. Okay, so this means for every sequence assigned of rationals, monotonic or non-monotonic, the limit that converges to alpha, this limit is a to the power of alpha. So this is well defined indeed. That's an important step. Yeah, and as I said, it's also valid whether Sn is monotonic or not. This proves that this is well defined, and in fact, for every sequence that satisfies this, this holds. And basically, what we have proven here is that it's kind of nice that we can just push the limit into here, into the, basically if you think of the exponential function, right, then you can just push the limit inwards, right? So this is what we proved. Look, it looks really beautiful. Like you can switch the limit and exponent, right? Okay, flip between them. So in particular, another thing that we need to show in terms of well-definedness. Now we have defined a to the power of alpha for every real number alpha by choosing a sequence of rational that converges to it, and we get the same limit. But now we need to prove that when alpha happens to be a rational number, right, then this result yields the same result that coincides with the definition of a rational power which we had previously. So in particular, since we've proved that the limit is independent of the sequence of rationals that we chose, we can choose the constant sequence of rational that converges to q, which now alpha is this rational number q, and therefore this constant sequence is going to have the same value as a to the power of a rational number. So indeed, now this is truly well defined. So a to the power of qn is just the constant sequence, and this value is indeed how it was, how the rational exponent of real number was previously defined. So this new definition of the real exponent actually extends. It's independent of the sequence that we have chosen. And for rational numbers, if this real number happens to be rational, it coincides with the old definition, and we can use any sequence of rationals now that converges to alpha. It doesn't have to be a monotone sequence. So this is indeed very well defined, and this definition now of the real exponents is valid. Okay, so that's so in particular, yeah. So we've proved that. So that's an important step. That's a very important step towards future results. So what we're going to prove next is that for a, which is a real number, a positive real number, we pick alpha to be a real number, and pq any two rationals such that alpha is greater than p and smaller than q. And then this desired property, which we know for rational exponents, if you ignore for the moment a to the power of alpha here, then if a is between 0 and 1, then the greater the exponent, the smaller the result is whenever a is smaller than 1. And when a is bigger than 1, then the bigger the exponent, the bigger the end result. And so here it's nice to have this property that this is valid now not only for rational numbers but for real numbers. But currently it's just a real number that is between two rationals. But then you can see how this result would extend to any pair of real numbers, right? Because if you have two real numbers, then there is a rational number between them. Okay, so this property that when a is greater than 1, then the bigger the exponent, the bigger the result, is valid now for all real exponents. So this is an important step, and the same for all real exponents. When a is between 0 and 1, then the bigger the exponent, the smaller the result is. So now we're going to prove it. So which of the sequence of rationals are n, right, rationals, such that this satisfies this property and would converge to alpha. Now the important thing is that it's for all the values it's between p and q, but it's not such a hard restriction. You can see how all the elements of the sequence of rationals can be chosen in this interval, and I give you like a direct way of how such sequence could be constructed of rational numbers that converges to alpha. So basically, what we look is we take this alpha-centered, so to say, interval when you have alpha, and here you just take the distance of alpha from alpha to p, and then divide it by n, and then subtract this to alpha. This is the end of the interval, and the other end of the interval is going to be you take this alpha, and then you take the distance from q to alpha and divide this by n. And so at each step we're going to choose the sequence of rationals in this interval. So indeed, like if we make a computation to show that this family of intervals is indeed contained in this parent interval pq for every value of n, I mean, intuitively it's clear because, you know, from alpha you take the distance here from alpha to p and divide by n. But if you want to prove it formally, then you compute the common denominator here. Here you have n times alpha and then minus alpha. So it's n minus 1 times alpha and plus p. And then here it's going to be by the same computation q and plus n minus 1 times alpha. And so the next step would be is to know that since alpha is actually bigger than p, then well, let's just see it. So since alpha is bigger than p, then this is going to be bigger than p, and since alpha is smaller than q, then this we have here is going to be smaller than q. Okay, so why is that? Well, because here if you were to replace alpha by p, since alpha is greater than p, then you make the result smaller here, and then we have here on top is n times p over n, which is just p, and similarly for the other end of the interval. So what you get is that this family of intervals is indeed contained in this parent interval pq. So now if a is greater than 1, then for every rational number, that's the property of rationals, which we know and already established, we have that, right? And since the sequence of rational, we picked it to be to converge to the limit alpha, then we can now use the limit arithmetic theorem. So we've now proved that every sequence of rational that converges to alpha, then a to the power of n is going to be a convergent sequence. It doesn't matter which sequence we pick, and the value is going to be the same for every sequence, and then the sequence is going to converge, and the value to which it converges is actually the definition of what it means to take a to the power of alpha. So now this is a convergent sequence, so by the limit arithmetic theorem, we have is that a to the power of Rn is going to be smaller or equal to a to the power of, here it's supposed to be q, a to the power of p, and smaller or equal of a from a to the power of q. Okay, and so by the same argument, when a is smaller, is greater than 0 and smaller than 1, we have here is this is going to be between, in the other way, yeah, here I got it right actually. So it's a to the power of p, and it's a to the power of alpha greater than a to the power of q. Okay, good. So now using the density of the rational number, so what we have here is this weak inequality. It's this is bigger or equal, and this is bigger or equal. The same here is smaller or equal, smaller or bigger or equal, whatever you choose to call it, but the inequality here is not strict. But now we can use the nice trick in that we can now pick rational numbers between p and alpha, since p is strictly bigger than alpha. Since alpha is strictly bigger than p, and q is strictly bigger than alpha, then we can choose rational number in between those and then use the property which was established for the rational numbers. So now since we have this inequality and this inequality is strict, then we can just choose other rationals, p prime and q prime in between, that is separating alpha and p and alpha and q, and then we can apply the same result that was proved, so to obtain that, okay, if p is rational and p prime is a rational that is bigger than that, then it's going to be bigger than this. And since p prime is a rational that is smaller than alpha, then a to the power of alpha is bigger or equal to that. And the same here, a to the power of alpha is smaller or equal to that. And here we have a strict inequality. So now what happens is that what we've obtained for a to the power of alpha is actually a strict inequality for a to the power of p and a to the power of q. Hopefully it was clear enough. So this implies that for alpha bigger than 1, we have is this inequality, and for alpha between 0 and 1, the same argument applies we get this inequality, and now the inequalities are strict.
Now that we've proved this important inequality, we'll use it using the sandwich theorem, and we'll prove the following important theorem, which we're now going to essentially generalize the definition of the real power in terms of not only rational convergence sequences, but rather as the limit of real sequences, sequences of real numbers. So, and in this case, we will see that it's consistent with the previous definition because we can view sequences of rational numbers as sequences of real numbers that happen to be rational, right? So let's see the following theorem. The following theorem says that now we can take alpha n to be a real convergence sequence that converges to the limit alpha. And then for every positive a, right, we would have that the limit of a to the power of alpha n would converge to a to the power of alpha. And this means, this is something very nice that I want to show here, is that alpha is the limit of the sequences of the sequence alpha n, and this actually states that we can interchange the limit and shove it like inside, right, to switch the limit here, because alpha is this limit and this is a to the power of alpha. And so just an important remark of what we're going to prove and see in the future is that this is essentially showing that the exponential function is continuous. We could conclude from here that the exponential function is continuous. So later in the course, we will see that this is equivalent for the function f of x defined by this being continuous, that we can interchange the function and the limit, but it is stepping a bit forward, right? I just wanted to give you some flavor of the more advanced material that we're going to cover. Yeah, so now that we have, defined what it means to take a real power of a real number, of non-negative real number, then now we can define and we can say that a to this power of alpha is the same even if we take any sequence that is convergent of real numbers, which is equivalent to the continuity of the exponential function, right? The exponential or a to the power of x. Okay, so let's see how we're going to prove it. And as I said, this inequality that we've proved previously is going to be helpful because we're going to apply the sandwich theorem. So we start by noting that we can find sequences Pn and Qn of rational numbers such that alpha n, the sequence would be bounded by Pn and Qn, and the distance between Qn and Pn can be made arbitrarily small, but we'll take it to be 1 over n. Essentially, this all can be done using the fact that the rational numbers are dense in the real numbers. It is equivalent to this statement that every interval contains a rational number and an irrational number, or any interval with endpoints which are rational would contain a real number. So anyway, we'll show exactly how to construct those sequences, right? So that would be the first step. So how can we do it? So we can choose Pn in this interval, and again, we are using that every interval of real numbers would contain a rational number because the rationals are dense in the reals, and we can choose Q in this interval, right, of alpha, between alpha n and alpha n plus 1 over 2n. Therefore, we would see that Pn is strictly smaller than alpha n, and Qn is strictly bigger than alpha n, and the difference, the distance between Pn and Qn is less than the width of the entire interval, which is twice 1 over 2n, which is 1 over n, and this would complete this step, right? Okay, so let's continue. So now this way we can construct those sequences, alpha n. So this sequence Qn satisfies that it's between alpha n and alpha n plus 1 over 2n, and similarly for Pn. And now, since alpha n is convergent to alpha by the assumption, we're going to apply the sandwich theorem, and in both cases this would imply that, first of all, the sequence Pn and Qn are convergent to the same limit alpha. That's quite obvious, right, because of those inequalities that we have over here, and the sequence alpha n is convergent, so this is convergent to alpha, and this converges to alpha, therefore Qn has to converge to alpha, and similarly for Pn. So now the previous theorem implies that for any two sequences of rational numbers that are convergent to a real number alpha, a to the power of Pn and the same a to the power of Qn would converge to a to the power of alpha, right? That's the previous theorem that we've proved. So now the corollary implies that for every n natural, and so if a happens to be between 0 and 1, what we have is this inequality. So using this inequality, since a to the power of alpha n is between those now two convergent sequences, we can now, that's the corollary that we've proved, right? Basically, we can apply this inequality to where we have mixed sequences of rational and real numbers. So we have this inequality, and therefore now we can apply to it the sandwich theorem, and now remember that both of those sequences are convergent to a to the power of alpha, and therefore the sandwich theorem would apply that this sequence has to converge to a to the power of alpha, just as desired, right? And similarly, if a is greater than 1, then we have this inequality, and again the sandwich theorem comes to zero skew here. So in both cases, the sandwich theorem implies that the limit of a to the power of alpha n would have to converge to a to the power of alpha. So now that's an important step. We've actually now generalized the notion of the real power using sequences of real numbers, and we have showed that the function a to the power of x is continuous. We haven't defined continuity of functions yet, but I'm just saying it to give you some advanced flavor of what's about to come. Okay, so this is good. And now we're going to prove the following proposition using the fact that now we can use sequences of real numbers. We're going to prove the law of exponents, but now for any two real numbers. So if alpha and beta are any two real numbers, right, we know this for rational powers, right? But now we're going to prove it for the real powers. And while it seems obvious, remember that the real power is defined as this limit. First, it was defined as this limit of sequences of rational numbers that would converge to alpha and then to beta. And now we can use actually sequences of real numbers. So let's see how we apply the previous theorem and prove this result. So first of all, let us choose any two sequences of rational numbers. So Pn would converge to alpha and Qn would converge to beta, right? And then since for every natural n we have that those are rationals, so for rationals we already know the law of exponents, right? But the tricky thing is here is that when we want to prove that the same holds for real numbers, then we need to do this limiting procedure. Okay, so the limit arithmetic theorem now implies that if we take the limit, then so Pn plus Qn is a sequence of rational numbers which is convergent, and it converges to alpha plus beta. Therefore, this limit exists, and it's a to the power of alpha plus beta. Now, taking this limit, since this is a convergent sequence and this is a convergent sequence, then applying the limit arithmetic theorem, we get the result, and therefore this law of exponents is valid for real numbers as well as rationals. So that's an important step. Okay, and now let's prove another law of exponents that is valid for the real numbers, right? It seems obvious, but when you prove it the first time, you have to take all the steps. And again, this is known for rational numbers, but now to prove for the real numbers, we need to do this limiting process. So again, we can choose a sequence Rn of rational numbers that this sequence would converge to alpha. Okay, and then for every natural number n, we would have that. We have this law of let's say exponents, right? This law that a times b to the power of Rn equals to a to the power n times b to the power of Rn. And now again, to show that this is valid for every real number, and still the real power is defined as this limit of sequences of rational numbers that converge, right? As we've seen before. So now we can use again the limit arithmetic theorem and say, okay, so a times b is this real number, and so taking the limit and Rn converges to alpha. So now we already know that this limit equals to this, almost by definition, right? And now again, since this law of exponents is valid, then we can apply again the limit arithmetic theorem to this case, and since Rn converges to alpha, then we get the result. Okay. So congratulations if you made it so far, because it's been quite technical, and now it's time to make it even more technical. And the following result, even though it would seem obvious, is kind of the hardest technically to prove. Okay. And so let's see the result now that we've built all the machinery and established the properties of real exponents. Now we're ready to prove the following lemma. So whenever we have an, which is a positive sequence, that converges to 1, then for any real alpha, then this limit is going to be 1. Now, it seems kind of obvious, right, intuitively, but why is this result hard? Because remember that an to the power of alpha, when alpha is a real number, is in itself a limiting process, right? So, you know, we would need some properties of real numbers that we have established and to use some inequalities here to actually prove this, right? Because we have, so to say, limits of limits, right? Because an to the power of alpha is defined by some limiting process, and then we take the limit when a of n goes to infinity of an. But it seems intuitive that if an converges to 1, then an to the power of alpha is supposed to converge to 1. But the proof of this is going to be, you'll see, it's kind of technical. Okay, so suppose that alpha is positive for now, because negative alpha handled just the same way. Suppose that we've proved it for for positive alpha, then we apply the same property to 1 over a to the power of alpha, and then use the limit arithmetic theorem by the same property, and then we have, by the limit arithmetic theorem, the result. So suppose that alpha is greater than 0, and then we fix epsilon, right? And we need to prove, according to the definition, that an to the power of alpha can get arbitrarily close to 1, provided that n is large enough. But we need to figure out how big n has to be, right? So since the letter epsilon is reserved, we will use the letter eta for now, right? As this another parameter. So eta would be the parameter, or like the epsilon for the sequence an, right? But epsilon is fixed. This is the important thing to remember here. So now, since n converges to 1, then for every eta between strictly bigger than 0 and strictly smaller than 1, there exists an natural number n of eta such that for every natural number n that is greater of n of eta, this holds. Basically, this is restating the statement according to the definition that n converges to 1. Now, the thing is that, remember, we need to estimate n to the power of alpha. Okay, and now we're going to use properties of real exponents that we've proved. Okay, and let k be any natural number that is greater than alpha. Then what we have is the following inequality. Now we're using the property that we've proved for real exponents, right? So now alpha is a real exponent, and then 1 plus eta is greater than e to the power of n. Therefore, by the property that we've proved, for the real exponents, an to the power of alpha is going to be smaller than that. And again, the same property for the real exponents. Now we can treat k as a real number. Since k is greater than alpha, and this is greater than 1, then this holds. And similarly, in the other direction, this is smaller than an, but strictly positive. So we have this inequality. Nothing to worry about here. Everything is strictly positive. And since this is smaller than 1, and again, we can treat k now as a real exponent if you wish, then this would be smaller than that. Okay. So now we have, we're using the properties of the real exponents, which we've worked very hard to prove. Okay. So now we'd like to estimate this value, and remember, we want to choose, the idea is that we want to choose eta in such a way that when eta is small enough, because we have absolute control over eta here, then essentially an to the power of alpha is going to be between 1 plus epsilon and 1 minus epsilon, right? That's the idea. right? So we need to estimate and to see how we can choose eta dependent on the exponent k and alpha. We'll see. All right. So for now, we can use the Bernoulli formula, and then 1 plus eta to the power of k is just, expanding the binomial formula here. And then since eta is between 0 and 1, then the greatest eta to the power of 1 is actually the largest number here, right? Because eta is smaller than 1, then eta squared is smaller than eta to the power of 1, etc. And the first exponent, when m is 0, then the first term is 1, and we factor it out here. So when m is 0, we have this 1, and then all the other exponents from 1 to k are, strictly bigger than 0 exponents, strictly positive. And now we can say that this sum is smaller than that, right? Because remember, eta is between 0 and 1, and therefore eta to the power of 1 is the largest one. So we just replace eta to the power of m when m is between 1 and k by eta, which is larger in this sum. So we have that this is smaller than that, right? And then the sum of binomial coefficients is going to be smaller than 2 to the power of k. Yeah, basically we'll see it shortly. So again, the justification here, the last inequality follows since, as I mentioned, that since eta is between 0 and 1, then for every m1 and m2 that are natural, if m2 is greater than m1, then we have this, right? This is kind of obvious from properties of real numbers, because this is just equivalent to that eta being smaller than 1, okay? And now to the second identity, right? We've actually proved that before, but 2 to the power of n is 1 plus 1 to the power of n, but then extending this by the binomial formula, we get the sum of all the binomial coefficients. So the sum of all the binomial coefficients is just 2 to the power of n, right? And now if we return to the previous formula here, we have actually this sum which goes from 1, but if we add the positive term here, which is just 1 here, right? Then this term, everything is positive here, is going to be bigger than that because we have an extra summation term, which is 1 over here. And then we can say that all this sum is just 2 to the power of k, right? So all of it is going to be smaller than 1 plus 2 to the power of k times eta. Now that's an estimate for, if we go back, then we've estimated this expression, okay, in terms of k and eta. And now we will also need to use the extended version of the Bernoulli inequality, which we've proved. So yeah, sorry for that. Okay, let's go back to estimating this expression. So now eta is between 0 and 1, right? So 1 minus eta, here the expression is, if you look at it as 1 plus x, then x here is bigger than minus 1, or bigger or equal to minus 1, but we never actually touch the lowest threshold of 1 plus like minus 1 here, so it's strictly bigger than 0. But nevertheless, now that we have the extended version of the Bernoulli inequality, then we have that 1 minus eta to the power of k is greater than 1 minus k times eta. And then here is another obvious fact that we use, that 2 to the power of k is greater than k. You can prove it by induction, but you can prove it in many other ways. Basically, here when you start here, like think of it as starting from 1. Here you each time add 1, and here you each time multiply by 2, right? But I think previously we have proved already, even in this lecture series, that 2 to the power of k is strictly bigger than k. And if we were to replace k by 2 to the power of k here, know that we're subtracting here. So here we are subtracting a bigger term. Therefore, this is smaller than this. Hopefully this is clear enough. So now we have another estimate, okay? I know what you're thinking, this may be negative, but I mean, we'll choose eta in an appropriate way, so this is positive and exactly behaves as we wish. But for now, yeah, we have used this inequality, and now let's make a quick summary of what we have. We have that for every eta between 0 and 1 here, and natural k, which is greater than alpha. And if you forgot, alpha is the real exponent. Remember that we want to prove that an to the power of alpha converges to 1 whenever an converges to 1, and an is a real sequence. So whenever k is greater than alpha, then there exists a natural number n of eta, such that for every n greater than n of eta holds this inequality. An to the power of alpha, which we wanted to estimate in the first place, is between this value and this value, right? And now remember that we can choose eta as small as we please, because it's came from unwrapping the definition that n converges to 1, so eta can be chosen as small as we please. So eventually we like to find n of epsilon such that for every n that is greater than n of epsilon would have this. This is our goal. And if we manage to find such n of epsilon, then it would prove that n to the power of alpha converges to 1 as desired. Okay, so now remember that we can choose eta as we wish as long as it's positive, right? So we need to define eta as a function of epsilon such that for eta, which is a function of epsilon, what we would have for this appropriate choice of eta, remember we want to replace this by epsilon. So what we want for eta to satisfy is that 2 to the power of k times eta would be smaller than epsilon, and then this choice of n of eta, this n of eta, which is a function of epsilon, is at the end of the day just n of epsilon as we wish for. And so we see how we need to choose eta here, just solving the simple inequality. We will choose eta to be epsilon over 2k, right? And we must have that eta is smaller than 1 because we've invoked and used this property. In particular, we use this in this complementary part of the Bernoulli inequality that we used to the full extent. So now we can choose eta of epsilon to be the smaller between the two. 1/2 is just because it's smaller than 1. So we'll choose eta to be the minimum between 1/2 and epsilon divided by 2 to the power of k. And for this choice of eta, which is the minimum of the two, it is guaranteed that eta is between 0 and 1. And we have shown that for every epsilon, there exists n of epsilon, such that for every n that is greater than this n of epsilon, because eta is a function of epsilon, right, holds a to the power of n would be between 1 plus epsilon and 1 minus epsilon, and which means that a to the power of and to the power of alpha minus 1 is smaller than epsilon, which proves, according to the definition, that an to the power of alpha actually converges to 1. Wow, that was technical, right? Let's make a quick recap of that. So essentially, this result, which seems kind of obvious, right, is not obvious at all, and the difficulty here is that in the definition of the real exponent as this limit of sequences of rational numbers, right, and then we've proved the properties that this limit is well defined and is independent of the chosen sequence, etc. So remember now that we fix this real exponent, which is in itself defined in this complicated way, and we take a sequence that is varying here and converges to 1. Okay, so then we wanted to show that if n converges to 1, then an to the power of alpha would converge to 1. But basically, if an converges to 1, then we can choose eta. For every eta that is positive, we have this inequality, and then we'll choose eta in a sophisticated way. Here we've used the binomial formula and the properties of the real exponents. So an to the power of alpha would be smaller than that and bigger than that. Here we use the binomial formula and the fact that the sum of all binomial coefficients is 2 to the power of n. So we showed that 1 plus eta to the power of k is smaller than that. And we used the Bernoulli inequality to estimate this, to its full extent. So this is, if you think of it as 1 plus x, then x here is bigger or equal to -1, because eta here is strictly between 0 and 1. And then using this Bernoulli inequality, we have this. All right, so it works here because eta is between 0 and 1. And then we've used the kind of simple inequality well known that 2 to the power of k is going to be greater than k to establish this inequality. And so we prove that a n to the power of alpha is between 2 to the power of k times eta and 1 minus 2 to the power of k times eta, whenever k is any real number that is where k is any natural number that is greater than alpha, and eta is arbitrary. Eta is any real number that is greater than 0, right? And so we can choose eta to be as small as we please. So for choice of eta, as small as we please, we're guaranteed to have n of eta for the sequence an which converges to 1, right? And then for every n that is greater than n of eta, then an would be between 1 plus eta and 1 minus eta. Sorry if I'm saying this too fast, but this is just a recap. Right, so this is the goal. This is what the end result of what we want to prove. And now this implies that we can choose eta to be, we need it to be smaller than 1, and we need this to be smaller than epsilon. So this is the way we choose eta of epsilon. And now for every eta there exists n of eta accordingly, and then we choose eta as a function of epsilon. So eventually for every epsilon there exists n of epsilon, such that for every n greater than n of epsilon this holds, which proves that this limit is 1. Well, this is just the hardest and the most technical proof in this video lecture, and the other ones will follow. And now we'll use this result for the future, and then we'll prove many important results based on the hard work that we've did so far. Yeah, so we worked really hard to prove this result, and now we'll enjoy the fruits of the result. And basically what I mentioned at the beginning is the case where alpha is negative is following it directly by applying the limit arithmetic theorem to the sequence 1 over an. So if an converges to 1, the only thing that we need to say here is that an converges to 1, so since it converges to 1, then starting from some place it's close enough to 1, so it's strictly non-zero, and then 1 over n is well defined. And then for the sequence 1 over an, starting from the place where it's where an is strictly positive, we can apply the limit arithmetic theorem to this and get the result for the negative exponent, which is just the same, right? Follows directly by the limit arithmetic theorem. So now let's enjoy the fruits of this hard labor and prove the following result, which follows readily. Actually, this result now follows easily from the previous result, which was hard. So now the conclusion is the following one. Whenever we have a sequence an that is positive convergent sequence of real numbers, and basically an is greater than 0 for every n, and an converges to a, then for every alpha now, an to the power of alpha would converge to a to the power of alpha. Very nice property, right? Essentially, it's just like to say the continuity of this exponentiation process, but let's not jump ahead of ourselves. But it's kind of natural, right, that you replace here the sequence an by its limit, and then this is the limit of this. This is just beautiful, and it follows readily, actually follows easily. Why? Because we would consider this sequence Bn. Now, what can we say about Bn? Well, the sequence Bn clearly converges to 1 by the limit arithmetic theorem. So now for the sequence, right, by the limit arithmetic theorem, this converges to 1. And now we can apply the previous lemma to this sequence. So since an over a converges to 1, then this sequence to the power of alpha, according to the previous result, which we worked so hard to prove, then this limit is 1. We're just using this result, right? And then since this limit is 1, we can apply the limit arithmetic theorem again, but now to this sequence where we multiply it by a to the power of alpha. And now this sequence clearly, using the properties of the exponent, it's just identically equal to this sequence a to the power of alpha. But on the other hand, since this limit is 1 and this is a to the power of alpha, then this equals a to the power of alpha. Yeah, nice, isn't it? So we've just generalized. So and okay, let's prove another property of the real exponents. And again, this is well known for rational exponents, but the difficulty here, again, we're working very hard, is because the real exponent is defined as this limiting process. This is why establishing the same properties we have for rational numbers to real exponents is that hard. So again, we have to work according to the definition, and suppose we have some rational number. So first, suppose Q is some rational number, and we have a sequence Pn of rational numbers that converges to beta. So we're going to prove it in steps. But basically, we're now going to use limited arithmetic theorem and properties of limits that we've proved. Okay, now what we have here is a to the power of Q is just this number, right, a real number, and then we exponentiate it to the power of beta. And now, according to the definition of what means of the real exponent, this is just the limit of sequence of rationals Pn which converges to beta, and we've proved that this is well defined and is independent of the chosen sequence here. So this would be this limit of the sequence of rationals. And now for the rational numbers, we have this exponent well established long ago, right? It's just known property that a to the power of q to the power of Pn is equal to a to the power of q times Pn. And now again, by this sequence q times Pn is a sequence of rational numbers that converges to q times beta. Therefore, this equals to that, according almost by definition, right? Okay, so we have that. And now we're going to use what we've proved here as a lemma for the next step. So we have proven that for every real positive a, and for every rational number q, and any real beta, we have that a to the power of q to the power of beta equals to that, right? So it's just this mixed property for a real exponent and a rational exponent, okay? And now we're going to choose a sequence of rational numbers that converges to alpha, okay? This step is kind of clear because we want now to take another limiting process and replace the sequence qn to take the limit and replace it by alpha, which is the limit of qn, right? And you see, we're working hard because we are forced to work according to definition or by definition when we are establishing the properties of the real exponents. Well, once we've proved them, we can just use them, right? Okay. So since the sequence qn converges to alpha, what we have is that this sequence qn times beta converges to the real number alpha times beta, and therefore by the properties of the real exponents that we have already proved, we have that this limit is equal to that, right? Basically, we've just proved that, right? Okay, and so since sorry, here what I meant. So since limit of when n goes to infinity of a to the power of an, not such a successful choice. But if the sequence an converges to alpha, then this limit is a to the power of alpha. This implies, so again, a to the qn, qn converges to alpha. So a to the qn converges to a to the power of alpha, right? And now we have that, again, by this limit arithmetic theorem, we have that this limit equals to that, right? And not nice. We've just proved it, again, according to definition, right? Because we've proved that, and there is equality along the way. So we've proved this equality. And therefore, we conclude that a to the power of alpha to the power of beta equals to this limit, which, as we've proved, equals to this limit. But this limit, since qn times beta converges to alpha times beta, this limit exists and is equal to that. Therefore, we've established this property that we had for rational exponents, now for real exponents, and we had to use, there was no way going around the definition that we had to use and choose sequence of rationals that are converging to the limit. And now it's very technical and very hard, but now we can use this property of the real exponents. Well, we had to pass through the limit in order to establish and to prove it in several steps, right? This is hard. Okay. And other properties of real exponents can now be similarly established using the limits that we've proved. And I'll leave it as a simple exercise because, you have to do some exercises. But as you can see, you can verify that it follows readily from what we established so far. Okay, and now we will have the following lemma. If n is a positive convergent sequence of real numbers that converges to A, this is a lemma. So this limit is A. And suppose that this A is positive, right? Why is it positive? We probably guessed because we would like to take the sequence n to some exponent. And let Bn be a real sequence, Bn that converges to 0. Then what we have is that the limit of an to the power of Bn is 1. Okay, so this is nice. We're getting closer. Now note the difficulty level here, because now we have two sequences of real numbers, one to the exponent of the other. Now, using the properties of real exponents that we have already established, we can write that n to the power of Bn would be this product, and then essentially this is a product of exponents. Since here we have the same exponent, we can basically shove this a into this product, and then a reduces, and we get the same expression here. So we worked hard actually even to prove this intermediate results of the law of exponents for real exponents, and now we get to use it. So now note that an over a is a sequence that would be converging to 1, and then Bn by assumption is a sequence that converges to 0, and then here we have a to the power of Bn. A is a positive real number, and Bn converges to 0. So by the first lemma that we've proved in this lecture, actually states that this limit is going to be 1. So a is constant real exponent, and then Bn converges to 0, so this limit is going to be 1. All right, so let's see. So a is strictly positive, and then Bn converges to 0. So by the first lemma that we proved, this limit is 1. And now we want to, so the limited arithmetic theorem, by the limited arithmetic theorem, since this limit is 1, it would suffice to prove that this is 1. And this sequence inside, which is the base array, it converges to 1. So basically, it would suffice to prove that for this normalized sequence, n hat, right, we have n hat to the power of Bn, and this n hat is a sequence that converges to 1. So it suffices to prove by the limited arithmetic theorem that now I will stop calling n hat by n hat, and I would just refer to it as a n. So to summarize what we've said so far, it would suffice to prove that for any two sequences of real numbers n and Bn, with n strictly positive everywhere, and n converges to 1, and Bn converges to 0, then this limit of n to the power of Bn is going to be 1. And the difficulty here, so clearly n converges to 1, Bn converges to 0, so it has to really converge to 1. But the difficulty here is that now it's one sequence to the power of another sequence, right? Okay, now let's prove it. So Bn converges to 0, and since Bn converges to 0, it can get close to 0 as close as we wish, arbitrarily close. In particular, it would be its distance starting from some point from 0 is going to be smaller than 1. So starting from some capital N here, all the elements of the sequence are going to be between -1 and 1. And now if we look at the sequence an is strictly positive by assumption, right? And this implies that we can divide, again, we can look at 1 over an, and there is no danger here of dividing by 0, or the need if an was negative somewhere, then we need to reverse the inequality. But basically what we can do here is establish the following inequality, which is kind of easy and very nice. So the idea is the following one. So an to the power of Bn, so Bn is smaller than 1, so if an is bigger than 1, then n to the power of bn is going to be smaller than n to the power of 1, and if n is between 0 and 1, then n to the power of bn is going to be smaller than 1 over n, and everything here is well defined because n is strictly positive, so we're in no danger anywhere of dividing by 0 here. And the same for the minimum, right? And now note by assumption that the sequence n converges to 1 and it's nowhere 0, so by result we've proved early on in this lecture series, n would converge to 1 and so would 1 over n. This is the limit arithmetic theorem once again here. So this sequence would converge to 1 and this sequence would converge to 1, and basically by the sandwich theorem what we have is, okay, this limit is 1, this limit is 1, and by the sandwich theorem we have that the limit of this sequence is also 1. So we prove this result, but now it's going to get very satisfying, I think, because using this result we will be able to prove the main result of this lecture, and it's a very nice result. So suppose we have a sequence an which is strictly positive and converges to a real number a, right, and a is positive, then and bn is a convergent sequence that converges to the limit b, then what we're going to have is that a to the power of bn is going to converge to a to the power of b. Very satisfying and very expected, but again, without all the machinery that we have developed so far, it would have been impossible to prove. All right, so now let's see the proof, and the proof with all the machinery and all the hard work that we've done so far, is going to be quite natural and quite easy. So now that we can write a to the power of bn in the following way, so it's an over a to the power of bn minus b, and then times that. So using the law of exponents to write this times this times this, it's just going to be an over a to the power of bn, and then multiplying with this we get the same expression, so we didn't change anything. And again, we can use it because of the established law for real exponents we worked hard to prove, right? So now the primitive lemma implies, note that, okay, if we look at this expression, an over a converges to 1 and b is constant real number, so this sequence, as we take the limit of n to infinity, this would converge to 1, and this limits this sequence an over a converges to 1 and bn minus b converges to 0. So it's the previous result when we have the base sequence which converges to 1 and the exponent sequence which converges to 0. So the limit of such sequence would be 1 by the previous result. And then here we have the sequence which is, we have a constant positive real number a, and then sequence bn that converges to b, then this sequence would converge to a to the power of b. So now, using the previous lemma, let's just write down what we said so far. So this converges to 1, bn minus b converges to 0, so this limit is 1, yeah, and again, why is it 1? Because this limit is 1 by the limit arithmetic theorem, bn converges to b, so this limit is 0, therefore this limit, if we go back, is 1. Now, in the next step, what we're going to do is this sequence an over a converges to 1, and then b is this constant real exponent, so this limit is 1, but based on something we've already proved, right? Also worked quite hard to prove this. And then finally, this sequence, this limit is a to the power of b almost by definition, right? So if bn would have been a sequence of rational numbers to begin with, then this would have been the definition, this limit would be the definition of a to the power of b, if it's a convergent sequence. But basically, we worked hard to prove that this definition is well defined, and then we can use even the sequence of real numbers that converges to b, and the limit would be the same as the limit for the sequence of rationals. So that's a well-established result by now that we've already proved. So this limit is a to the power of b, and we've proved the main result. Yeah, it's really satisfying. So now applying the limit arithmetic theorem, what we get is that, we wrote an to the power of bn in the following way. The limit of the sequence is 1, the limit of the sequence is 1, the limit of the sequence is a to the power of b, so this limit is a to the power of b, as you would expect. So basically, the conditions here is that we need an to converge, we need bn to converge, and then for the exponent to be well defined, what we need here is that the sequence n is strictly positive everywhere and convergent, right, to a non-zero limit, and that's it. And basically, it's really satisfying that if an converges to a and bn converges to b, then the limit of n to the power of bn converges to a to the power of b, right? Very nice. This is the main result. This is like the highlight of the whole lecture and this hard technical lecture, now we can use this result. All right. Okay, and now something like a few words about infinite exponents now. Something that is kind of obvious for when the exponents are natural or rational. Now we can generalize it for arbitrary exponents, which are sequences of real numbers. So basically, if a is greater than 1 and alpha n converges to infinity, then as expected, a to the power of alpha n would converge to infinity. And if a is bigger than 1 and n converges to negative infinity, then this limit is going to be 0. And similarly, I mean, those results 3 and 4 are just falling from 1 and 2 by the limit arithmetic theorem. But basically, if a is between 0 and 1, then alpha n converges to infinity, then a to the alpha n as expected, this limit would be 0 and this limit would be infinite. So let's prove it quickly. So if a is greater than 1, we can write it as 1 plus something positive here, and as you've guessed, we're going to invoke the Bernoulli inequality, which was quite useful in this lecture. So we're going to work according to the definition. So let m be any positive real number. Basically, we need to show that a to the power of alpha n can be as large as we please, basically bigger than any m we choose in advance. So we can write this in the following way. Now, for any k that is natural, right, we have by Bernoulli's inequality, we've used several times so far, then 1 plus h to the power of k is going to be greater than that. And then, okay, if we continue the proof, we can choose k so that this inequality holds. Basically, it would suffice to choose k to be bigger than this and to be a natural number. So this choice of k would suffice. If we choose m over h integer value plus 1, right, then this is going to be greater than m over h. And then m over h is greater than this because we just, reduced the number here, the numerator, right? So choosing k of m in the following way guarantees that 1 plus kh is going to be greater than m. Okay, and now since we chose a in the following way, then for every alpha n that is greater than k, what we have is that a to the power of alpha n equals to this, and then by the law of real exponents that we've proved, since the base here is greater than 1, then we have this inequality, right? And this inequality works now for real exponents as well. And now this would be greater than 1 plus kh, and then the choice of k, the following choice guarantees that this is greater than m. So basically we need to show now that we can choose n accordingly, such that for any n greater than n of m, a to the power of alpha n is going to be greater than m. Okay, so now since alpha n converges to infinity, right, then k of m, we chose it, so k is a function of m, and then we look at n of m, which is n of k of m, but eventually this is a function of m. And then for every n that is greater than n of m, what we would have is that alpha n is greater than k, which implies, by the whole derivation that we've made, that a to the power of alpha n equals to this, and this is greater than this by the law of real exponents that we've proved, and then this by Bernoulli's inequality is bigger than that, and then by the choice of k it's going to be bigger than m. And okay, so we've proved that for any n that is greater than this n of m, this holds, which proves that this limit is infinite. And now another implication, so if alpha n would converge to negative infinity, right, then minus alpha n would converge to positive infinity. And since a is greater than 1, this implies that, okay, this limit of 1 over a to the power of alpha n, which is this limit, right? So again, 1 over a to the power of alpha n, and here we have a to the negative alpha n. So negative alpha n converges to positive infinity, right? So a to the positive to the limit of positive infinity is infinity. So what we have here is that 1 over a to the power of alpha n converges to infinity, which proves by the result that we had that this limit is 0, right? Since 1 over the sequence converges to infinity, then this limit is 0, right? And 3 and 4 follow from applying parts 1 and 2 in a similar manner to 1 over 8. right? And that's concludes the lecture. So thank you for surviving for and sticking for that far. That was very hard and very difficult, but now we have a very solid, very good foundations of the real exponents.